Okay, hey, welcome back. This is Lagrange Multipliers. We'll just start you out with the theorem. Lagrange's theorem. And basically what it is another way of solving these optimization problems where you have a constraint equation. In particular, this theorem will imply that the gradient of f evaluated at these critical points will be a constant multiple of the gradient of g. And from this and the constraint equation, you'll produce a system of equations that you'll be able to solve. Okay, right. So why does this work is probably the most important thing here. What you want to do first is represent the constraint function with a vector valued function. So take this constraint function, g of x comma y, which equals c, which you could also think of as one of our what the heck do they call those? A level curve. Okay, so g of x, y equals c. It's one of these level curve things. We'll need that fact here in a second. Okay, so let me get rid of this. And of course, okay, so there we go. So take this constraint curve. So first off, this is a constraint curve, but it's also a level curve. Represent it with a vector value function. So we'll call it r of t equals x of t comma y of t. Okay. All right. Then we're going to kind of put these component functions into the optimization function, okay, and then call that some other name, and it'll all be dependent on t. Okay, so substitute sub in x of t and y of t into our optimization function, which is going to be f of x comma y, and call it h. Let's just say and write it as h of t, which will equal f of x of t comma y of t. Okay. Right. So if you have a nice extreme value, so you take somehow you're able to take the function and put the constraint function in and remove one of the variables and get the partial derivatives and find the critical numbers. If you take one of those critical numbers and put it in here, given all these conditions, h prime of t will at that point will equal 0. Okay, so inputting an extreme value, which we'll say is at t sub 0, we note h prime of t sub 0 will equal 0. That's from Calc 1. If you have an extreme value and you put it into a function and the derivative exists, it's going to equal 0. Okay. Okay. So from what we learned about the chain rule, we also note h prime of this t sub 0 will equal the derivative of f with respect to t, which will be, from the chain rule, the partial derivative of f with respect to x times x with respect to t, plus the partial derivative of f with respect to y times dy with respect to dt. And from above, of course, that also will equal 0. Next, then, what is that? What is this thing right here? Next, note this fx dx dt plus fy dy dt that's just a dot product of the gradient of f and the derivative of r of t. And it's all supposed to be at this particular extreme value, but if you don't mind, I'm not going to write out all the little x sub zeros, y sub zeros, t sub zeros. Okay. Anyways, if you note that this thing equals 0, and you remember chapter 11 material, you'll note that these two guys are orthogonal. Okay, so hence the gradient delta f is orthogonal to this tangent vector r prime of t. Okay, so now the part about level curves becomes important, because we note this constraint curve, which is a level curve, is orthogonal to r prime of t as well. And that's from Theorem 13.12 over here on the right. If you click on that hyperlink, you'll go back in time to that theorem. So we note r prime of t is orthogonal to the level curve g of x comma y equals c, and so the gradient of g will be parallel to the gradient of f. Okay, so the gradient of g is parallel to the gradient of f, and so you have that statement for in Lagrange's theorem. The gradient of f is going to be a constant multiple of the gradient of g at that extreme point. And from there, you get a set of equations and you can solve. Okay? Okay, so, right. You may need to go back and review that Theorem 13.12, but hopefully that kind of gives you some sort of idea of what's going on. The book will give you some geometric intuition. I'm not sure, I'm not sold on that myself, but it's there. Let's dive into the exercises and see what's going on. All right, so there's not too many of them. Let's look at number 2. I want to maximize f of xy equals 4x plus 4xy plus y with the constraint function 4x plus y equals 200. Okay, this will be your g of xy. If you want to set it equal to 0, you can. So you'd have g of xy is 4x plus y minus 200, which equals 0. Let's make this the video quiz while we're at it. Okay, so let me mark that down in my notes. This is the second video quiz. If you missed a video quiz in 13.9, it was question 5 from WebAssign. Anyways, this is video quiz set number 6, and this is the second question in video quiz set number 6. So this is problem 2 from WebAssign. I just want to put that in my notes. Okay. All right, so you need the gradients for each of these functions. The gradient of f is going to be 4 plus 4y, and then the gradient, the other component is 4x plus 1. The gradient of g is going to be 4 and then 1. Okay, so the system of equations that you kind of have to solve then will be 4 plus 4y equals 4 lambda. 4x plus 1 equals 1 times lambda. So you're just equating the components. Okay, equate those two, but put a lambda on the 4. Equate these two, put a lambda on the 1. And then the third equation, because there are literally x, y, and lambda, 3 unknowns, you need 3 equations. So the third equation just comes from the constraint equation, 4x plus y minus 200 equals 0. Okay. From this, you should be able to solve for all the variables. Depending on how ambitious you are, you can take this one that's solved for lambda and plug it into this one. So I'm kind of doing a substitution method, and you get 4 plus 4y equals 4 times lambda, which is 4x plus 1. This will be 4 plus 4y equals 16x plus 4. and the 4's will cancel from each side, so you get 4y equals 16x. Y must then be equal to 4x. Then I can take it and put it into here, so you get 4x plus 4x minus 200 is equal to 0. So 8x is equal to 200, and then x is 200 over 8, which is 100 over 4, which is 25 for x. And then y is 4 times x, that's 4 times 25, which is 100. And then you put it back into your optimization formula, the thing you were trying to maximize, 25, 100, and that will give you your answer, right? So it'll be 4 times 25 plus 4 times 100, 25 times 100, and then plus 100, and that should equal 1,200, assuming I did everything right. Okay. So the problems are pretty much all like that. There's not really too much of a deal. You may get caught up in trying to solve these systems of equations. Like this one, 3 equations, 3 unknowns. Some of them can be nonlinear. So let's take a look at, I don't know, let's try number 4. Maybe that will be interesting. We'll leave it at that. That'll be the last question I'll look at, and I'll let you go. But you want to maximize f of x, y, z equals x, y, z. The constraint function is x plus y plus z minus 6 is 0, so that's going to be your g function. Get your gradient. So the gradient of f is going to be yz, comma xz, comma xy. The gradient of g is going to be 1, 1, 1, apparently. And then your constraint equation, again, x plus y plus z minus 6 is 0, or equals 6 if you'd rather. Right? So your, I guess, equations, you're now equating the gradients. So you get yz equals 1 times lambda. You get xz equals 1 times lambda. You get xy equals 1 times lambda. So you have 4 equations and 4 unknowns, and you have to solve that. And this is nonlinear. Okay? So you just do what you got to do to get the job done, honestly. So here I'm going to solve for, I guess, y. So y is lambda over z. Here then, x is, let's solve for z, shall we? No, that's, I want to solve one for, let's solve this one for z. Okay, so z is equal to lambda over x, and this one, let's, I don't know, solve it for x, right? So x is equal to lambda over y, and this will be kind of weird. So what I'm going to do is plug this guy into here. So I'll get y equals lambda all over x. Okay, what does that equal? That's just x, right? So you know, I can now kind of plug this one into here, and I have then z equals lambda all over x, which is lambda over y. So z equals y. So I accidentally wrote z there. So what? Well, that means x equals y equals z. They're all the same. And you could go back then to this equation and do x plus x plus x is 6. So 3x is 6. So x is 2. So y is 2 and z is 2. And you see that's my answer there. So yeah, it may be a little bit weird, but just keep in mind you're not doing anything new. It's just solving systems of nonlinear equations. You should have done that in pre-calculus. Okay? They can be weird. There are more types of problems in the book. 13.10 I didn't go into. There's so these are, I think they have some applications in here you you can take a look at. They also have Lagrange multiples with, we kind of did the 3-variable version. Optimization. Guess I don't have enough homework problems. Here's one with 2 constraints. So this is the only one that's kind of different. But yeah, so 2 constraints are going to have more of this. You have 3 gradients basically, and then you use lambda and mu. It's the same process. You'll develop systems of equations, and then you'll end up solving for your unknowns. Okay. Okay, but I don't think there's any of those in the homework, as far as I know. So let's leave it at that, and as usual, I'll see you next time. I think I gave you the video quiz this time. I didn't forget. It's number 2. Okay, awesome. I'll see you later.